You get it? Yeah. Okay. I couldn't hear the beep because there was a that was happening at the time that covered up the beep, which I accept. But anyway, I will start. Dear Father, we thank you for this day. I thank you for the students. Just pray with us today. Help us to understand more about Gaussian elimination, Lord. In your name I pray. Amen. All right. So here we go. Examples of row reduction. Example 1. Suppose I have A equal to 1, 1, 1, 0, 0, 1, 1, 2. There we go. Let us row reduce this thing. So, yeah. So to start with, this one's already done. Like the initial 1, 1 spot, it's already done. So I go on, because it's already cleared out below. So next up, that's my next pivot position. There's nothing below it. I'm already done with at the start, I'm already done with the forward pass. Embarrassing. So all we have left to do is to clear out this 1. So we do row 1 minus row 2. And I think I sometimes use lowercase r's and I sometimes use uppercase r's. Of course, you should use lowercase r's, otherwise I'll take off points. That's a joke. It doesn't matter. All right, 0, 1, 1, 2. In fact, at the start of my notes, you'll notice that there are some really cleverly teched things where there's parts of the row reduction which have been like faded out as it's going down. And there's like these long tildes and things. That's all written by my brother. I stole it from a handout of his. So that's why the notation's a little bit different there. That's the other popular notation for row reduction, which I think maybe Dr. Smith also uses. So, okay, I shut up, and that's it. This is it. This is the reduced row echelon form of A. Oh, I don't know. There are a lot of James Cooks, much less Cooks. At this institution, there exists another James Cook who's in charge of admission to the medical school, something like that. I do. On occasion, I get these incredibly polite emails from potential medical students. They go on, full of proper English, very sirish, like the sir this, sir that. It's really something. I feel so important. You should just respond to them and feel like you're accepted. I usually, respond you're accepted. I hadn't thought of that. No, I usually just respond, I'm not the James Cook you're looking for. And just leave it at that. But anyway, so that's it. Now, I thought we were talking about systems of equations, right? So here's example 2. What if we had A with a row with a column of zeros at the end of it? What would happen if you put a column of zeros? Well, nothing really. You do the same row reduction, and see what happens with a column of zeros, rather, if we add it to the end, if we adjoin it to the end, is every row operation you do, what does it do? It just takes it swaps zeros, it multiplies 0 by a non-zero number, it adds a linear combination of zeros to 0. It stays 0. So if you have a column of zeros and you do row reductions, it stays 0. All right? There's some sort of preservation of columns going on in this whole process, right? Like a column of zeros stays a column of zeros. So there you go. This is the reduced row echelon form of A with a column of zeros concatenated. And that serves my purpose to talk about a corresponding system, right? Let's talk about the solution set for this problem. So at this point, actually, it's not clear You guys, well, let me say this. So this could be the augmented coefficient matrix for, well, excuse me, this could be the augmented coefficient matrix for what system? Maybe x1 plus x2 plus x3 equals to 0, and x2 plus x3 plus 2x4 equals to 0. Can you guys even see that? Good grief, look at this, horrible. Sorry, I have spranoed the board. Let's see here. Sorry, sometimes it's not a pejorative. It's just a description of making a smudge on the board. So anyway, that system has that augmented coefficient matrix, right? And then this says what? This says x1 minus 2x4 equal to 0. And this says x2 plus x3 plus 2x4 equals to 0. All right? So in this problem, the pivots are the first and second columns, right? So the pivotal variables in this case are x1 and x2. Pivotal variables, x1 and x2. Non-pivot variables, what are they here? They are x3 and x4. So our custom is to use the non-pivotal variables as parameters in the solution set. So here's a claim. Actually, here's a truth. Can always solve for pivot variables in terms of non-pivot variables. There is some fine print attached for consistent systems. If it's an inconsistent system, well, you can't find a solution. Now, you can always solve for the pivotal variables in terms of the non-pivotal variables. So in this problem, that means x1 is equal to what? X1 is equal to, what did you tell me, 2x4. And x2 is equal to minus x3 minus 2x4. So the solution set to this system has more than one thing in it, right? Now the question is context, right? This is a system of equations over what field? So I mean, we can say this much. Then solution set is equal to solution set. So what we got is we've got 2x4 comma minus x3 plus 2x4 comma x3 comma x4 such that x3 and x4 are in the field over which we're solving these equations. I mean, I didn't tell you what field it was, right? It could be the real numbers, it could be the rational numbers, it could be the complex numbers. These are choices, right? In any of those cases, if it's an infinite field, right, a field with infinitely many elements, then the solution set has what? It has infinitely many elements, right? If you wanted to think of it geometrically, it's like a plane. The solution's like a plane in 4 dimensions if we're talking about an infinite field. Suppose the infinite real field. What if the field in question though wasn't infinite? What if f, for example, was say just z2, which has 0 and 1 in it. I'm using the notation 0 bar equals to 0 and 1 bar equals to 1, if that's okay. Yep.
Why is it negative x3 plus 4?
Oh, because I made a mistake? Thank you. Yeah, there's no like extra secret algorithm that at that point you just randomly add minuses. No. It's just a mistake. Yes, thank you. So in the case that we're working over this finite field, Z2, what are you looking at? If we were working with that, we'd have, just like I wrote. And by the way, we don't have to use x4. We could use like s and t. So s minus t minus 2s. What was my t s such that s and t are either equal to 0 or 1. To be clear, s and t in Z2. So some people like to use other letters for the parameters. I typically will just use the variables themselves because it's easier to see where it came from, right? But those are just parameters for the solution set. It's really, you could use a different letter other than x3 and x4 if you wanted to. However, it is our custom to write solution sets using the non-pivot variables as parameters of the solution set. All right? So if I ask you to solve a system and to write the solution set in standard form, I'm talking about this convention. We write the pivot variables as linear, as dependent variables depending on the non-pivot variables. The non-pivot variables are independent variables. Yeah.
Do you have to write it using both non-pivot variables, or can you just use one of the non-pivot?
You have to use both. You have to use all the non-pivot variables. Now, so this we could actually list. How many are how many does the solution set have? It's got 0, 0, 0, 0, right? We could put s equal to, oh goodness, what's 2 equal to? 0. I'm sorry, in Z2, Z2 is kind of annoying. So yeah, this is just 0 in Z2, and that's just 0 in Z2. So I can safely put 0. I know in advance that I just need to fill in the other blanks, yeah? Because that first one's always 0. Let's see, so I could put t equals to 1. So I get minus 1, s equal to 0. So I get minus 1, 0. I seem to have lost my place. Look, I've stupidly added a what? A comma here. Was that comma really here? No. Idiot. Me, not you. 0, minus 1, 0. Son of a gun. This is not complicated. How did I find a way to make this complicated? All right, 0. No. So this is 0, t, 0. I keep putting the comma in there. Grief. 0, t, t, s. Ay, ay, ay. Goodness gracious. So the solutions are 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, and finally 0, 1, 1, 1. So what I'm using, Z2 is weird. So like x is equal to minus x in Z2. So you can just drop minuses in Z2 because you can add twice the thing and you get back where you started. And multiples of anything multiplied by 2 is 0 in Z2. All right? So that would be the solution set here. How many things are in this solution set? You can count? 4. What is 4? I mean, it's 2 times 2, but unfortunately, what I'm looking for here is 2 to the 2. If we solve this over Z3, what would it look like? Over Z3, the solution set would have, you could say x3 and x4 in Z3, right? And this gives 3 times 3 equals 3 to the 2 solutions. So over a finite field, the number of solutions is going to be the size of the field raised to the number of free parameters. So if it's if you have 2 parameters and it's a field of order 3, you're going to get 9 solutions. It took me a long time to write it out, but over a field of order 2, we got 2 to the 2, 4 solutions, yeah.
Sorry, you lost me for a second.
Oh.
Where are all those zeros and ones coming from again?
I'm just plugging in s equals to 0 and t equals to 0 or 1. There's, it's either 0, 0 or 0, 1 or 1, 0 or 1, 1, and that gives me these 4 cases. Uh-huh. Let's see here. Suppose we're looking at x plus 3y plus 2z equals to 1, and x plus 2y minus z equals to 0. All right? Yep.
Sorry, just to clarify that one.
Sure.
If you have something over like z mod n, your solution set would be n times the number of variables that you have?
So the theorem is over f with p elements if ax equals to b has k free variables. So the free variables are aka non-pivotal. The non-pivotal variables are free or independent, all right? Then solution set has, well, let's say the size of the solution set is equal to p to the power k. Again, assuming it's consistent.
Okay.
If it's inconsistent, it has 0 solutions, but this theorem should become more clear as we look at more examples. It's really just an immediate consequence of Gaussian elimination and reasoning through what the solution set looks like in terms of the number of pivots versus the number of non-pivot columns. If k equals to 0, what's p to the 0? 1, right? So if we have no non-pivot columns, right, that means that there's a unique solution, right? In the case of an infinite field, though, we either have no non-pivotal columns and there's a unique solution, right? Or the system is inconsistent, no solutions, or we have a non-pivotal column, which means we have a free infinite variable, so there's infinitely many solutions. Those are it's a different story whether it's finite versus infinite. So this here, what would our, if we're going to solve this over, let's say, Z5. If we're going to solve this over Z5, then let's see here, 1, 3, 2, 1. 1, 2, minus 1, 0. There's my augmented coefficient matrix, right? And I would do row 2 minus row 1. What's that give me? Am I right? Well, oh, wait a minute. What's 2 minus 3? Thank you. Yeah. Very good. Okay, great. And then my next move would be to do row 1 plus 3 row 2, which would give me 1, 0. What's minus 9 plus 2? Minus 7, yeah. Minus 2, I think. Now, it depends on what you're after. If you're after the reduced row echelon form, we're not done, right? So since I'm trying to show you reduced row echelon form, let's go ahead and do minus R2. There we go. 1, 0, minus 7, minus 2, 0, 1, 3, 1. Now, so if I call this initial matrix A with B, then what we've shown is that the reduced row echelon form of A with B, the augmented coefficient matrix, I've got 1, 0, minus 7, minus 2. We're working over Z5. How could we write that a little bit differently? We could say 1, 0, minus 2, yeah. And I'll write the minus 2 as 3, 0, 1, 3, 1. So what I just did was I added 5 to minus 7 because we're in Z5, right? So this is minus 7 is equal to minus 2 in Z5. In Z5, well, I think that's all I did. So now at this point, this is a much nicer. What does this say? This says, hey, this says that x is x minus 2z is equal to 3. The second one says that y plus 3z is equal to 0. Once you guys get comfortable with what we're doing, we often don't even write down that step. All right? Pretty soon from now, you'll just go from this to writing, okay, so x is equal to 2z plus 3, and y is equal to minus 3z. Yeah.
Why were you able to change the minus 2 on the far right?
Because minus 2,
Yeah, and then you didn't do that for minus 7, though. You just looked at it as
well, minus 7 plus 5 is equal to minus 2.
Yeah, so why didn't you just do that again? Or can you not do that again? Just so that it's all positive?
Because I knew I was going to add the 2z to the other side. I could, sure. You get many choices. The reason I didn't, though, is because I knew I was going to add the 2z to the other side, and I wanted that 2z in my...
So it's just a matter of personal preference.
Exactly. Now, so that's the solution. What's the solution set? Now, this is for what? This is for z and where?
We're gonna one. The y plus 3 equals 1.
Oh, I've somehow changed my 1 to a 0. Yeah, that's not good. Thank you. Very good.
So minus 4.
Indeedly doodly. Excellent. Thank you. So that's the solution. What's the solution set? So we've got 2z plus 3, 1, and thanks for pointing that error out before I got to this step, because otherwise I would have been, I can't afford to pull a hair out. Let's see here, z and z5. So there you go. That's the solution set. How many things are there? If you believe my theorem, my claim was that there should be the size of the field, which here is 5, raised to the number of free variables. How many free variables are there in the solution? There is 1. That free variable is z. So supposedly there should be 5 solutions. What are those 5 solutions explicitly? Well, we could rewrite it this way. We could say that what we're really looking at here is 3, 1, 0 plus z times 2. I guess I could do, I'm sorry, ignore what I'm doing. It's not, it doesn't help us. Unnecessary foreshadowing. Let me stop. You guys tell me, what are the 5 solutions? I'll put z equal to 0. That gives me a 3, a 1, a 0. Z equals to 1 gives me what? 5, which is 0, minus 2, which is 3, 1. Put z equal to 2, I got 4 plus 3, which is 2. What did I just say? Put z equal to 3, right? Z equal to 1 minus 9 is minus 8, which is 2. I said z was 3, right? Yeah. Put z equal to... Oh, did I do that?
And for z equals 1, it should be... Never mind.
All right, you know what? Fine. I will do a middle step. So we've got 3, 1, 0. 5, minus 2, 1. 7, minus 5, 2. 6, 3. Putting z equal to 3, 3, 6, 9. 3, minus 8, 3. And finally, put z equal to 4, 8, 11, minus 11, 4. And then, of course, we could simplify these mod 5, right? To not go nuts in my grading, when I ask a question like this, I often ask you to leave the answer in terms of quote-unquote positive residues. And that's what I'm doing at the moment. In other words, use the number between 0 and 4 to represent the Z5 number. There we go. Those are the 5 solutions to this system of 2 equations and 3 unknowns in Z5. All right, I'm going to stop talking about Zn and just focus on the reals for the rest of the lecture, okay? Yeah. What if we had A equals to 0, 0, 0, 1, 1, 2, 3, 8, 0. Suppose you want to do row reduction on that. How's it go? See, in this case, we've got a column of zeros to start with. So we simply cannot make the first column the pivot, the first pivot, right? It's impossible. And the second, well, so first thing we're going to do is we're going to do row 2 swapped with row 1, right? And so if we do that, we get, I mean, you can do various things, but this is what I do. 1, 1, 2, yeah? It would have been smarter. You know what I should have done? I should have brought up row 3. That would have been lazier. But what's done is done. What's done is done. All right, so now we've got a pivot in the proper place, namely here. And we want to clear out the 3. What do? R3 minus 3 row 1, right? So that gives me 0, 1, 1, 2, 0, 0, 0, 0, 0, 0, 5, minus 6, yeah? And so I've cleared out under my first pivot, right? And then I learn that I need to do something. In order to get the second pivot, I'm going to have to flip row 2 and row 3. I have to swap row 2 and row 3. So that gives me 0, 1, 1, 2, 0, 0, 5, minus 6, and then zeros. All right. And then what comes next? Yeah, the backwards pass, various options exist. One thing you could do here would be to do row 1 minus 1/5 row 2. As you can see, my rows all of a sudden have become lowercase. Interesting. 0, 1, 0, and then, of course, we're looking at a 2 plus 6/5, yeah? All right, so final finishing blow, row 2 divided by 5. And we got 0, 1, 0. What did you tell me? Oh, 16/5, yeah. And then we got our 0, 0, 1, minus 6/5, 0, 0, 0, and 0. And there you go. This is the reduced row echelon form of A. I told you guys last time that after you're done, you'll always have pivot columns, which are the standard basis put in order. See how that's happening? Here's your E1. Here's your E2. This guy is non-pivotal column, right? I claim that this algorithm always gives us a unique result. All right. Any questions about this one? Yep.
Why is the last column not true?
Because it's not E1 or E2.
Okay.
I mean, it doesn't. The last column does not have a leading one. So pivot columns, if you look at a row, if we're talking about a pivot column, it has to have a leading one from the perspective of looking at a row from the left. So if I look, well, from the left to the right. So this has a leading one. So if I look from here, that's the first one, right? That has a leading one because if I look from the second row, that's the first one I find in the second row. The last one does not have a leading one. All right? Yes, if there was a system to talk about, if there was a leading one in the last, if there is a leading one in the last column of an augmented coefficient matrix, that means that the underlying system is inconsistent. Let's show that for a specific example. Before I get to that example, though, a stupid example. What's the reduced row echelon form? It is not. So the reduced row echelon form of A is 1, 3/2, 2, and 0. As you see, I've somehow added commas. I'll put them in the original one so we feel better about our life. But yes, it is just row 1 divided by 2. That is the single and only needed row operation. Yeah. Yes?
You said this was a stupid example, but that 4 these numbered image looks suspiciously like a top hat.
It looks like a top hat.
Have we forgotten something?
Oh, you made me say that word, monster. This was such a pleasant lecture until just now. Fine. They'll have their pound of electronic flesh. Here it is. Here you go. There, be counted. All right. So, and where's the standard basis in this one? What's the pivot column? You got to use your imagination a little bit, but this one is E1 in one dimension, and that is the pivot column here. These guys are non-pivot columns. All right, anyway. Example 5, again stupid, but V equals to 1, 2, 3, 4. How about row reduction of a vector? What happens here? What does it break down to? Very silly, but I would just do, row 2 minus 2 row 1, row 3 minus 3 row 1, row 4, why did I do 4? I could have done 3 vector just the same, anyway, too late. Row 4 minus 4 row 1, what do we get? This brings us to E1, and that is the reduced row echelon form of V. Please don't ask me what the corresponding system is to this problem. What's the corresponding system of equations to this problem? And yet, this is a meaningful row reduction, all right? We can do row reduction for matrices which don't necessarily immediately appear to be anything to do with a given system, all right? I can't even say if it's, it's just a row reduction. I don't know what system of equations would correspond to the vector V. I don't know. I could do this. Let me not. So getting back to Nathaniel's comment, let me do another actual not stupid example. Yeah, I guess here. All right, here we go. What example am I on? Oh, 6, yeah. How about x plus y plus z minus 2w equal to 1? And let's see here, 2x plus 2y plus 2z minus 4w equal to 2. And finally, 3x plus 3y plus 3z minus 6w equal to 4. All right, so augmented coefficient matrix is 1, 1, 1, minus 2, 1, 2, 2, 2, minus 4, 2, and 3, 3, 3, minus 6, 4. Now, sometimes it's helpful to the reader when you do something like this, especially if the equations you're given don't have the letters all in order. Like sometimes you're given equations which have like x first in one and y first in another, and the variables are all jumbled. These are not. But if they were, it's sometimes helpful to like write a little x, y, z, and w here, just to announce to the reader that, hey, that's the x column, that's the y column, that's the z column, that's the w column, all right? Sometimes you'll see that. All right, so we can do row reductions. What do we get? Row 2 minus 2 row 1, right? Row 3 minus 3 row 1, what do we get? Not the most exciting row reduction. You'll forgive me for not making a problem that took us 20 minutes to calculate. But then again, you probably don't want to be here 20 minutes from now, right? Just guessing. So, done. That's the reduced to echelon form of the augmented coefficient matrix, right? And in this case, indeed, this does have the interpretation as a system. And so I stated the initial system. What is the final equations? What's the final solution say? So the first equation would seem to say that x is equal to 1 minus y minus z plus 2w for, right? And if it wasn't for that pesky last row, we'd just be like, for any x, y, and z, right? We'd have a solution with 3 free parameters that have infinitely many things. But what's raining on our parade? Yeah, that last, yeah, exactly. What does that last row mean? Right. This says that 0 times x plus 0 times y plus 0 times z plus 0 times w is equal to 1. Well, that's not a solution, right? I mean, 0 cannot be equal to 1. And so there you have it. No solution. So for an augmented coefficient matrix, if after we do the row reduction, if the final column, the rightmost column, is a pivot column, we're in trouble. The rightmost column it can't have a leading one in it, all right? It has to be a non-pivotal column to be consistent. Now, so in summary, for an infinite field, what's going on, if you think about it, we're starting with A with B, right? And after a bit, we've got like E1 stuff, whatever, E2 stuff, E3, eventually we get to, our last pivot, let's say EK, and then the last column. But there should be zeros. This is like, K plus 1 to M. This would be the consistent case if you had K pivotal columns, right? So this is a M by N plus 1 matrix if we're talking about M equations and N unknowns. And, I'm sorry, let me, I can't count today worth anything. Before I get to this general counting, let me do one more example. Otherwise, it won't make as much sense as it needs to for you guys. So example 7. If we have the augmented coefficient matrix of 1, 1, 2, 3, 4, 0, 0, 1, 0, 6, and 0, 0, 0, 1, 2. All right. There isn't much to do here because we don't have much time. But if that was the augmented coefficient matrix for a system, I would do a row reduction, right? And I get like what? Row 1 minus 2 row 2. Wait a minute. What's 4 minus 12 is minus 8. Am I done? Not quite. I still got to clear out this 3. So row 1 minus 3 row 3. that minus 14? So this one's a little bit more interesting in the sense that, so we have pivot, pivot. Right, so in this problem, it turns out that x1 and x3 are pivot variables, but x2 and x4, oh, excuse me, x4 as well, very good. Thank you. So just x2 is non-pivot, right? Or you could say it's a free variable. x2 is free. We can use it as a parameter for the solution set. And this is the general pattern. If we're looking at an m by n system, right? Something like ax equals to b. We've got a with b, right? After a bit, we reduce it to something along the lines of, this. And this will have k pivot columns. And I shouldn't say k pivot. I should say n minus k pivot columns and k non-pivot columns. I really want to count the non-pivot columns because those are the parameters in the system. That's what was tripping me up in my previous counting. So in that one, we have 3 pivot columns and 1 non-pivot column. N is equal to 4. Generically speaking, you'll have, n minus k pivot columns. The remaining k are non-pivot. Those give you parameters in the solution set, assuming it's consistent, right? Here I'm assuming the case that the last column is not a pivot column. This is all stated carefully in the notes as a theorem, but yep.
Why would x4 be a pivot column?
Why would x4? Because it's got a leading 1. It's the leading 1 here. There's no way to move that 1 out of there using row. I mean, you could move it up or down, but it's going to be, the location of pivot columns is not up for grab. That's a unique outcome of the Gaussian elimination. And you notice, again, E1, E2, E3. Yeah. Anyway, I have many more examples in the notes. I'd like you to look at them. I have good news. I won't be here Friday.
I'm going to miss you.
Why is that? Do we have a class?
No, we do have class. Dr. Smith is going to guest lecture on a topic known as elementary matrices. And these are very nice, and I'm sure he will do a good job. So
Have a good day.
that will not be videoed, obviously. All right.